So what are our grade up to, come on. What are our grade updates? So we've had the post-exam 1, post-exam 2 grades. We also have our post-exam 3 grade now in. That post-exam 3 grade factors everything that I had in my control. Okay? So if you submitted things a little bit later, okay, those scores aren't updated, which means your post-exam 3 grade isn't accurate for the most part. Okay? But what I went through and did is said, okay, based off of everything you've done, we've got the final writing project, which, to be honest, I just went through and said everybody got full credit. Like, you still got to do it, for the record. But I'm not grading it in a way that I think would remove points from you, for better or worse. Okay? So more than likely that AI project, everybody's going to get full credit. So that's what I assumed to calculating the final grade, which then means there's only one thing really left. Okay? There's the final exam. We do have paper, homework, and active, but I'll just assume that those maintain the same average that you've been maintaining. Okay? So if I go through and do that, that gets me to a post-exam 3 grade on what I would say what you could reasonably expect at the end of the semester. In that assumption, what I went through and did is predicted what your final score would be, your final exam. To get that, I took the average of all 3 exams. Okay? The final exam will have 70 questions, so it says 70 points. It's not points, it's 70 questions. So the number under final average prediction, or average final prediction, is the number of questions that you would get right based off of your average score for exam 1, 2, and 3. Does that make sense? Okay. So then we've got some kind of interpretive stuff that goes after it, which could be helpful in determining how much effort you need to go through and put in for the class. Okay, so let's look at a post-exam 3 grade. Let's say it says C. You get a little bit more information than that, but when I look at it, I have to dig really deep to get a percentage, a numerical value. Okay, but let's just say it says C. It says the average final prediction is 35. Okay, for those counting, 35 is 50%, and you might be like, well, dang, how is that a C? Isn't that failing miserably? That's roughly how the class is structured, so that if you get a 50% on the exams, but perfect everything else, you get a C. Right? Like, that's the intent behind it. Okay? So let's say it comes down with that. Okay, that's what you're expected. So if you look at that C grade and you're like, okay, I'm happy with a C, that's all I want. I'm expected to get a 35. That's you maintaining what you are currently doing. Okay, that's what that roughly is. Okay, but let's say you're not happy with a C, you want to go up to a B. Okay, that's this advanced final prediction. Okay, so let's throw some potential numbers in there. Let's say to advance, let's go with the most painful or awkward one, you see nothing written there. Canvas might even show a dash. What does that mean? This means in my calculations, based off of what I have access to, I can't see you getting a score on the final that would allow you to advance a letter grade. Okay? What that really means in kind of more specific terms is that the C that you are currently expected to get is the bottom of the barrel. You're scraping the C borderline. Okay? That's what that blank would mean. Okay? It does show up in other cases. It can show up if you have a B. Okay? It's possible that I can't see a final exam score that would jump you to an A. Okay? Does that make sense? Okay? If you have an A, that's going to be blank as well because you can't advance, just for the record. Okay? So let's pick something that's a little bit less depressing. Let's pick something like, let's be super optimistic. Let's go with a 36. What does that mean?
Out of what?
70.
Oh.
These are all 70 questions. The final is going to be 70 questions. If you get a 36 out of 70, I mean, yes, but it's different. It's more than just pass. You go up a letter grade. You go from a C to a B. If you hit 36, I guarantee that I will give you that higher letter grade. That's what that means. Okay, does that make sense? Okay. Do people see numbers in there? I'm a little nervous that maybe I didn't post it. There are no, okay, as long as there's numbers there, that's okay. So really what that means is your C is a very, very high C. Okay, because you don't have to change much to get that higher letter grade. What if it drops to, or not drops, but says 50? Okay, that's probably meaning you're at a lower end on the C category. Okay, so there is some kind of interpretations that we could run here. Okay, first and foremost, to go up to a B, does that look like an easy jump? Okay, that's going to be a pretty significant input on your part to ensure that you maximize getting those questions. Make sense?
Yep.
Okay, so what do you do with that information? Well, there's two outcomes that I see. The outcome that I would hope for is that you now really crack down and try and maximize, learn the content so that you maximize and you advance a grade. That's what I want. Okay? Just because I want it doesn't mean you have to want it. But that's what I will try and push you to do, is to get that content to go up a grade. If you're looking at, I got a C, I've got to work really, really hard to get up to a B, no. Okay, that's fair. Okay, I accept. I'll be disappointed, but who cares? Right? You shouldn't care about my disappointment. I can care about my own disappointment. Right? So you can just decide, I'm not going to work that extra hard. I'm just going to try and make sure that I can hit that 35. Right? This now flips the coin a little bit, because maybe 35, like, where is that C? If now you've decided you're just happy with the C and you're not going to go for the B, well, you just want to maintain that letter grade. That's that next category, that maintain category. So now we would see another number potentially there. Okay. The depressing one, if we see a dash or no score, this is a really depressing one. Number one, it's not a C. What it is a not passing grade. Okay, that's what it means. If you're looking at that maintain, there is no, you're in a non-passing category. You can't, I don't think it makes sense to maintain a D or an F. Okay, so if you're not seeing something there, you have to be looking at that advanced category, or you can have a conversation with me about withdrawing. That's okay too. Okay, but let's take a look at that advanced number. Let's say we see a number of 25. What does that mean?
You get 25
to keep your C. Your current effort is a 35 expected. To just maintain your C, you need a 25. What does that mean you can do for the rest of the semester? You could probably just coast. Okay? You've probably got other classes, you've got life, you've got other things that factor in. You could just coast and kind of ignore it. And we're going to look at those numbers in a little bit more depth in a second, but that's ultimately what that means. Okay? If you look at it and instead it says 34, what does that mean? Your average is expecting you to hit a C, but you have very little wiggle room. You're looking at a question difference between a C and a D. Okay? So this means it's not just maintenance. You should be working a little bit harder so that you've got a little bit of buffer on that approach. Make sense? Okay. I'm more than happy to go through with anybody in the class their individual numbers and say what I see or how I would interpret it. Okay. Remember, there are some pretty big sections of grades for a few of you that are missing from this calculation. If you did play posits late posits haven't been factored in. Okay. The AI project part 1, I think everybody is graded for, but part 2, not everybody was graded when I went through to enter it. Those are now, actually, sorry, those aren't factoring into this because I just assumed everybody was going to do it and get it perfect when I factored this graded. So play posits, paper homework. I don't know where our paper homework is at for the whole class. Okay, the active homeworks. There are still other, we still have play posits, we still have active, and we still have paper homework. In this calculation, I'm assuming you maintain your current average for those. Right? If you improve in those categories, these numbers will change around in your favor. If you disprove, it's the opposite, get worse, not do as well on those individual assignments, these numbers are going to go in a not favorable direction because you now have to make up those points. Does that make sense? Right. So again, I will go through with anybody who wants to those individual scores. I don't want to do that in class because I think that's just nerve-wracking and embarrassing. I would never want somebody to do that where other people could hear. So we can figure out a place where we can sit down and talk through it. We could even do it in lab and just go off in the corner somewhere. I think that would work. Next thing I want to address, and let's just leave these numbers up here. It is going to be a 70 question exam. That's a lot. Okay? That's probably more questions per minute than our actual exams. Okay? If we look at kind of question breakdowns, not by a huge amount, but by a significant amount. Okay? Some of those questions are full-on repeats. Have you been going back and looking at exam 1, 2, and soon to be 3 to ensure that you know why you got questions wrong and what the correct answers are? If you have been already, you've already done some of the work because you will see those exact same questions again. The answer choices may shuffle around, but you'll see some of those exact same questions. Okay? I said baseline 10 questions per exam. That's roughly half of the exam you already have. You just have to make sure you spend the time to memorize those answers if you wanted to push that direction. Does that make sense? Right? There is going to be more after it. The more after it will be a spread. That will be both in this future content and going backwards too. Maybe I look back at it and be like, I didn't ask a question about this. I feel like I should ask a question about that in Fisher projections. I didn't ask enough Fisher projection questions. I'll ask another Fisher projection question. Kind of, sort of? Okay. So 70 questions, that's a lot. I don't think anybody has to answer 70 questions. Well, everybody should answer 70 questions. Not everybody should genuinely attempt 70 questions. Right? If you're this person that just wants a C, your magic number is 34. Do you think you need to answer all 70 questions? No, you need to answer 34 correctly. So it's not a 70 question test anymore. It's a 34 question test. Okay? With 34, I can't do math, 36. 36? 36 distractors. Okay, so ignore those other questions, find your 34, get those 34 right. Okay? If you wanted to advance to the 50, it's still not a 70 question test, it's a 50 question test. Find your 50 questions. Okay? So what I'm giving you the setup to do is to be able to triage your way through the exam and say, these questions I'm not going to worry about, they're just too hard, I'm going to focus in on the questions that I can answer. Does that make sense? Questions about any of that? You just laughed. Why'd you laugh at me?
I just do bad at time, so.
So, and then that's pushing back to find your questions. Right? And I don't know that we've had a whole lot of conversations about that within our tests or with any of these tests. You should not be taking them linearly. You should be taking them based off the question that you think you know the answer to. So skip around. Okay? Move through. If you're looking at a question, you're like, oh my God, this is so hard. I can't figure out what to do next. Stop looking at it. You were already going to get it wrong. Okay? If you're stumbling and tripping in your brain, all you're going to do is continue to stumble and trip in your brain and ruin your prospect to get other questions right. Okay? So as soon as you feel tripped up, you move on. Tripped up, move on. Tripped up, move on. Once you've made it through the whole exam, now you're in the situation where now you actually have to work through and start fighting through some of those trip-ups. Okay? But first address the whole exam at face value. Make sense? Questions?
Not about that.
That's
but,
fine.
You haven't given us the homework for this week.
I have not.
Okay. Because there isn't one, or because you haven't done the act?
Actually, we did have and by we, I think it was just Jennifer and I had a conversation about it. The active is supposed to be due this week, but then it would be due on Sunday. You would have spent the whole Thanksgiving working on chemistry, which, I mean, yes, you should be spending some time, but actually getting points assigned to you for that might be a bit rough. So what will end up happening is I'll build out active to be due, not this Sunday, but the following, with paper home. So I think every weekend after Thanksgiving, we're gonna be looking at, thinking, was like, no, I didn't think that. You should be seeing both an active and a paper homework come through. Right? Because we're gonna need that practice to kind of get through. We can decide within that practice what you wanna see. Is it just new content? Is it going back to old content? To me, all of the paper homework, I would be going backwards. I'd be looking at exam 1, 2, and 3 for paper homework. For the active homework, I have to put a majority towards the newest content, so you have some practice there. But if you guys want to see older stuff, I can put older stuff in there. Right? To the end of the week summary of questions, I will be trying to build that, yes. I just haven't done that yet. I'm still struggling to get lectures to where I want them to be. Right now, all I've got is the play posits kind of built out, and I've got some of the summary slides built in. And I think what a lot of our lectures are going to be is just looking at kind of the summary and saying, what do these functional groups do? What should we be thinking about? How should we be addressing it? So there aren't going to be more slides. I still have to get content. Fuck me, ow. I hope that didn't get recorded. I guarantee it did, but oh well. Ow, that hurt. Yes. So homework will be there eventually, just not quite yet. Struggling to get time.
Is there a way to get like the end of the week for older content as well? Because we didn't have that one.
Ooh. That is a fair question.
Like what the test was, like example of like what the test
Send me an email so that I've got a paper trail. On a Thursday, I would say you could tell me at the end of class, and that would make sense. But we're not going to meet this Thursday, and I'll forget because we've got lab right afterwards. So send me an email so that I've got that sitting there, and what I will try and do is go backwards and pull stuff. Because yeah, that's a good point.
When do you apply the extra credit?
It's a good point. Good point. Extra credit is not applied at all with any of this. So what will happen is at the end of the semester, exactly like I went through to determine this post-exam 3 grade, I will assign grades. Once I've assigned grades, I will then go back and say, okay, within 2% of that grade cutoff, is there a score there? Yes, there's a score. And you go, why aren't you saying names? I only look at the scores when I go through to assign grades. I remove the name from my vision because I don't want to build bias, which is going to be hard with a really small class, unfortunately. But I try to limit that as much as possible. I look to see if there's a name within that window or a score within that window. Then I see the name. Then I go back and check the extra credit. If the extra credit's there, I go back all the way back to that score and I just add 2%, and it immediately jumps you above the grade cutoff, and that's where you're at. So that way, it is strictly extra credit. If you didn't do it, it's not a tick against you because it's done after I've assigned the grades. When I go through to assign grades, I usually will try and drop the cutoff. So it does put a few scores on that button in that space. It does kind of depend. Just because I always look from the higher scores, but if we saw something like this, 90, so there's a bunch of scores. Where do you think an A belongs? Not including extra. These are just the scores at the end of the semester. If you were looking at those scores, who do you think deserves an A? Has anybody been an 89?
Yeah.
Yeah, what happens when you get that 89?
You get a
I mean,
My teachers always make me do.
If it's 0.5, they'll usually round it sometimes.
how do you know they round it?
My professors never rounded it.
Mine
Did you ask?
have. Yeah.
I've asked them before,
Yeah.
they've never rounded it.
When I look at this, what I see is 2 emails. Easily fixed. Now I don't have 2 emails. Right? I don't have to deal with that. And this is why I don't bring the names into it. Because if there's a name on it and I'm like, oh, I don't think they worked hard enough, I'm putting a bias in it. So I remove the name aspect from it and I go, is an 89 versus a 90 really all that different? No. Is that really fair to say that 89 deserves a B and that 90 deserves an A? I think that's pretty crap. Okay? So what I'll look for is where there breaks. Okay? So 88.7 to an 86, or even 89, dude, that's like rounding. Like I'm going to get an email. So what I'll do is look for those breaks, where I see those breaks. Okay? When I've got a break, I'll get that cut off. Small class, it can be very hard to find those breaks. Okay? So sometimes I may very well say, okay, 90 and above, and fully expecting to get that email. Okay? But that's where what I would do. Okay? So first and foremost, I would say this. There's my cutoff for A's. Okay? 2% is an 86 within 2% of an 88. Yeah. So I circle that. I scroll all the way to the left where the name is. Okay? In my Excel spreadsheet, I look at the name and go, okay, did you do the extra credit? Yeah? Plus 2%. That's not an 86 anymore. That's an 88. There's my cutoff. A. I don't get any emails. Because the 83 is like, well, that's 5% away from an 88. Like, there's no way. That fixes all the issues. And that person has proven by doing the extra credit that they deserve more credit. They did a bunch of extra work. Okay. That makes sense. So I believe it creates a more fair system within that. Why do some instructors make hard lines at those 90s? Okay. Ultimately, where I think that comes from is that they don't test or assess appropriately during the semester. Okay? What I mean by that is they gave a test where everybody scored perfect. Okay? Well, if everybody's scoring perfect, how do you differentiate the different people within the class? Okay? You can't. Which means they end up splitting hairs over where they're differentiating because they didn't do a good job of properly assessing differences in student abilities. But they'll go through and say, but you're curving, and that's mean to curve people off. It's wrong both ways. Find the way that best suits your preference as an instructor and what you're happy with. I'm happy not getting a whole bunch of emails complaining about a fraction of a point. So to your rounding, yes, I'll round. I just don't tell you I'm rounding. I just say the cutoff is slightly lower. And you go, oh, Lindsay's being so nice because you curve. I didn't want to hear you email me. That's a little bit mean. I didn't mean it like that. I looked at it and be like, I can't tell a difference in the quality of what you've submitted versus somebody right above you. I can't differentiate. Okay? This is the most I've talked through it. This 92 may be pissed that that 86 now got an A and they got an A. I think in the grand scheme, that's not that big of a difference. And I would fight. I would actually have a conversation with that 92 and be like, if you really want to have this fight, we can have this fight. You're wrong. I would tell them to go away. That person deserved the work. Kind of makes sense. Is it less scary or more scary? Hopefully it's less scary. So emailing about points within an assignment at the end of the semester is usually stressful. I will fully admit at the end of the semester assigning grades, I'm on the verge of tears every time dealing with grades. Because invariably I'll go through and I'll be like, that 83, once I bring in that person, I'll be like, they work so flippin' hard, why are they only that grade and not this grade? And get depressed. Or I'll look, and this happens less, I'll look at this 90 and be like, what the? That person proved time and time again that they could not communicate anything about the class. How are they getting an A in the class? So it happens both ways. Usually it happens people scoring lower than I wanted them to, but every so often there'll be someone scoring higher than I feel they should have. I I don't want either of those biases affecting the grades, which is why I removed the names from it. For this class, it's going to be this case, the 83 that way. I don't feel anybody is trying to manipulate the system and is somehow doing way better than they should. I also try to build a system that prevents that. So, other questions? Exam 3, while I could see value in going through it in class, we're just so far behind on all of this kind of content that we've got to kind of crank through that I don't want to spend any time in class on it. Please send me if you can't make it to office hours, send me an email. I don't know how to do question 4. Okay. Let me write a video. I'll even build a video for you. Say, here it is. I'll post it to YouTube. Everybody, hey, question 4, here it is. This is how you should be thinking through it, what you should have thought about and address. Okay? Yes, that takes more time. I would rather spend more time that you learn the content than less time and have you just forget it in a week. Okay? And because I want to do real fast scrolls, I'm actually going to close out of this. The way I kind of envision the rest of the semester, I think I wrote down somewhere and then changed my plan somewhere else. We've got our nonpolar pi bond reactions, so additions. There's technically 2 classes of additions, acid additions and electrophile additions. Okay? Those are split into 2 play posit videos, one directly on acid additions and one on electrophile additions. Electrophile additions, full disclosure, suck. Okay? You're dealing with weird atoms, weird chemistries, and everything just gets kind of bizarre and convoluted, and it's hard to hold track of all of those moving parts and pieces. Okay? Do the best that you can. This is where this kind of diagram is going to come into play, and we'll tweak it here in a little bit, but what you're trying to do is effectively just memorize what's on there. That diagram has some gaps within it because you can only show so much, okay, with an individual picture. So we've got our additions, technically acid additions and electrophile additions. What charge are acids?
You mean like the conjugate base with acids?
If you said you had an acidic solution, what would you see in that acidic solution?
Lots of H+.
Lots of H plus. So when we look at an acid solution, we're looking at positive charges. Okay? What charge are electrophiles? Also positive. So our electrophile additions and our acid additions are ultimately the same thing. We're just nuancing the differences just slightly, saying under the acid addition that we're talking specifically about hydrogens being positive. The electrophile additions are everything else that's positive. Okay? But ultimately, the chemistry more or less stays similar. Again, things can go wonky on us, but that's ultimately what's happening within those. After we do our additions, or our positive additions, if you will, what we'll move to is now polar pi bonds. Polar pi bonds are actually going to change the chemistry a little bit, and they're going to shift now to nucleophile additions. Again, we'll address why when we get there. Okay, once you have nucleophile additions, you can then do nucleophile eliminations that match right along with it. Okay? The electrophile additions don't do the eliminations in stacked because of a secondary consideration the polar pi bond brings in. Okay? So the way I sort of parse this in my head is that in those 5 lectures, what we've now just covered are 4. Okay? Today, theoretically, would be acid addition. Next Tuesday would be electrophile addition. Next Thursday would be nucleophile addition. The Tuesday after that would be nucleophile addition followed by elimination. And then the last Thursday that's our nucleophile addition and elimination. The last Thursday would hit us with electrophile aromatic substitution. Okay, the last reaction. Okay, that to me covers all the functional groups that you could possibly see. When we talk through fundamental OChem, that's what they do. They just do all of these throughout the entire semester, and it's largely just, here's the answer, here's the answer, here's the answer, here's the answer. And invariably you get students being like, but why? The but why is why we spent the first 14 weeks of the semester looking at structure, okay, looking at mechanisms, and then looking at the basics of what happens within substitution and elimination. Because what we're going to do for all of these reactions is apply those same 3 units back to this. Okay? And that's pushing the why. What I would argue is you don't, or what the course design argues is that you don't need the why, you just need the what. And if we're just going to ask the what, the course doesn't need to be 16 weeks. It just needs to be, here's all the stuff you should memorize. Memorize, now spit it back out. Which is effectively what we're doing right here at the end. Does that make sense? Right. So it will feel painful, but I would argue all we've done is condensed the pain into 3 weeks as opposed to 16. Okay? So, scroll all the way back up to the beginning. All of these you'll notice are listed as play posits because those play posits are intended to provide the fundamental basics behind how these things react and what they do. And what we'll talk through in class is now more the specifics, the what instead of the how that the play posits are doing. Okay? So when we go through and look at our first section, I'm actually going to delete that. What we're talking about is a non-polar pi bond. Okay? For it to be non-polar, what does that mean? There's no dipole. Well, when do we get dipoles? Difference in electronegativity. So our non-polar pi bonds then mean there is no difference in electronegativity. Okay? Because we took the periodic table and whittled that down massively, that really only puts us with one set of atoms that could appear in a non-polar pi bond, carbons. Okay? And to get to the pi bond, we must first encounter a sigma bond. So we'll take a sigma bond, and then we'll overlap with a pi bond on top, so to speak. Okay? What makes the pi bond? True, it is a pair of electrons. Where are those pair of electrons held for a pi bond? P orbitals, above and below. So when we're talking about our pi bond, we're talking about the electrons that are either located kind of above the molecule or below the molecule. Okay, those are the electrons that we're referencing. If we take a look at the hybridization of our carbon for a standard structure like this, it would typically be sp2 hybridized. Okay, so we just have 3 groups of electrons, the double bond connecting our carbons. If we were going to look at this more 3-dimensionally so that we could see those p orbitals up and down, we'd be talking about our groups, or those extra connections out here, being wedged and dashed. Okay? If we looked at just a pi bond, that's the iPad looking at it straight on. If we want to see the p orbitals, they're coming in and out of the plane, out of the iPad at you. That's not easy to see or draw, so we turn it so we can see the p orbitals up and down. Make sense? Okay. Now we want to consider how this would react. Okay, well, we have 4 ways that things can react. What are those 4 ways? Not main reactions, how a thing reacts. So if I look at a thing, I can say, that thing acts like this. Okay. So when we look at this functional group of our nonpolar pi bond, what we should be immediately trying to do is overlay this information of acid-base nucleophile electrophile to say how it might act. Okay? And actually, I'm going to rewind just a little bit before we get there. If we look at our system, we already got a clue as to what we're talking about. Which of these electrons are we going to talk about reacting? We've got sigma bond, sigma bond, sigma bond, sigma pi. Which of those are we talking about reacting? The pi. Why should we react to the pi? Say it again. Why are they easier to break? going all the way back to unit 1, what made up our pi bond? P orbitals. There are P orbitals. Okay, what makes up a sigma bond?
That's
S-type orbitals. When we look at the bond between our S-type orbitals, what do they look like? Whereas our P orbitals are these. What does that mean? The sigma can rotate because we'll always maintain an overlap in that process. The pi bonds can't rotate because we would break that overlap. So the whole molecule would have to rotate. Okay? This also does something else for us. What does it do to the energy of the orbitals holding those electrons? What's the difference between an s orbital and a p orbital? All the way back to unit 1.
electrons.
Yes, where the electrons are. S orbitals are lower in energy than P. What does that mean? When we go back to our nonpolar pi bond, what's the reactive thing? The pi bond. Why? Because it involves P orbitals, and P orbitals are naturally higher in energy than our sigma orbitals or S orbitals. So that explains why the pi bond reacts. Okay? If we want to push this now into our category, we're talking about the pi bond reacting. What is it reacting as? Is it an acid-base nucleophile or electrophile? And if we remember what the name of this unit was about, we actually have an answer. Okay? We said we were talking about electrophile additions. What would it mean to do an addition reaction to this?
Remove the pi bond.
If I do an addition, that pi bond would be gone. No more p orbitals. Okay? What reacted?
The electrons in the pi bond.
The electrons in the pi bond. What charge are our electrons? Negative. What charge was an electrophile? Positive. Is the pi bond acting as an electrophile? No. The pi bond is acting as a source of electrons. It's going to react with an electrophile. So we're talking about the electrophile addition. We're looking at a positive thing near the pi bond that's going to cause that reaction. What is the pi bond acting as? A nucleophile, because it is donating electrons to our electrophile. So the pi bond is really going to be a nucleophile. But what if that positively charged thing was a hydrogen? Is it now acting as a nucleophile? No. What's it acting as now? A base, because it's sharing its electrons with hydrogen. So when we're going through and thinking about all of these reactions and theoretically just this today's lecture, what we're saying is that pi bond must be sharing electrons with something positive. That something positive could be an acid, in which case when we do the addition reaction, what we're doing is adding a hydrogen onto the pi bond. Right? So the pi bond breaks it. But if we add a hydrogen to it, where do I add the hydrogen? Where do I want to put the hydrogen? Can I show a bond from the bond to the hydrogen? No. So where do I attach the hydrogen?
You just kind of floating out in space.
What does the curved arrow mean?
Transfer electrons.
It's not transfer of electrons.
Sharing them.
It's sharing. What does it mean to share electrons?
Create a bond.
To create a bond. Is the hydrogen floating out in space? No, it's bonded. What is it bonded to? Bonded to a carbon. Which carbon? And that's an interesting question. Well, where should I put it? Okay, well, at this point, can you tell the difference between those carbons? So does it matter where you connect the hydrogen? No, so just connect it. Ta-da, hydrogen. What happened to the other carbon? It has to become a carbocation. When we talked about the pi bond reacting, what we were doing is taking those electrons and effectively saying, here, this carbon, our left carbon, take the electrons so you can form a bond with the hydrogen. What happened to the other carbon? It lost its electrons. It still has that p orbital. There's just no electrons in that p orbital. Now, that's known as a carbocation. Okay? So now what has to happen?
Something has to neutralize the carbocation.
Okay, something has to neutralize the carbocation. What does the identity of that something have to... What's a characteristic of that something? It has to be negatively charged or have electrons, which means it's acting as a nucleophile because it's sharing with a positive carbon. So the net result is that we set up another reaction here, no longer an addition, because we've already broken the pi bond, but we now have to add something else here, some kind of nucleophile. So if we understand kind of the pieces of those things, how those things might react, we can start to make those predictions. Kind of get it? Okay. What we've drawn out now are officially mechanisms. Okay? And what we're trying to think through is how those mechanisms could occur. This is effectively what we did with SN1 and SN2. Okay? Except now we're speeding it up and just kind of saying this is how it happens and hope you don't fall drastically behind, which is moronic, because you will. Okay? Kind of, sort of? So when we look at a nonpolar pi bond, your focus is that it's acting as a nucleophile or as a base, which then means it needs to react with something positive first. Okay? Why can't the pi bond react with something negative first?
Because you're not trying to create a triple bond.
No, I liked your suggestion, a little bit weird. The pi bond is reactive because it's a source of electrons. Could those source of electrons get near more electrons? No. Okay? So our pi bond is the reactivity as the negative. It is our electrons, which means all of our reactions with nonpolar pi bonds are centered on that carbon sharing electrons or that bond sharing electrons out. They're always nucleophilic. Kind of, sort of? Okay. So if we now go back to the pattern here, okay, referred to as a spider diagram, we're starting at the center. In that center, we're looking at a particular type of alkene or nonpolar pi bond. Okay? But the reasons behind why we're picking that particular structure is because of the secondary chemistry that goes with it. That's our stereochemistry. That's our regiochemistry. If we think back to our SN1 and SN2 or E1 and E2, that's the complications of those reactions. That's the how. So we had to pick a starting structure that would allow those secondary considerations to manifest. Because if we just picked a normal, just alkene carbon-carbon double bond, we would never see that manifest. Okay, what do we mean by that? We actually already saw that. And that very first step that we drew out, we said we could place the hydrogen at either of those positions. And if there is no preference, this isn't an or, what is it? It's an and. Okay? What is the most reactive thing on our product side?
The positive charge.
The positive charge. Okay? So if we're going to look at this reaction functioning, it's going to react in such a way that I make the most stable positive charge possible. Have we talked about how positive charges could be more or less stable? Yeah? What did we talk about? Primary, secondary, or tertiary. What could you share around it? Sharing is probably better if we consider resonance within that system, but the primary, secondary, tertiary is a simple analogy. So we could go through, let's tweak it. Let's say we have another carbon right here. Does that mean the other three positions are empty? No, these other three positions are now defined as hydrogens. If we go through to look at our product, we've added that new hydrogen, RH. Right? Are both of those equally likely? No. Why not?
The right one's more stable.
The right one forms a more stable carbocation, which means when this pi bond comes out to react with that positive, what happens? It's not an and or an or, it's one product as this one. It's the more stable. Okay? Differentiating between these two is our regiochemistry. That regiochemistry is dictated based off the stability of where our charges are located. This is why we talk about stability of charges, so that we can apply that backward or now to our more advanced systems. So when we run this reaction, that one doesn't happen and I only get this one. Does that manifest in our spider diagram? Okay. So lots of stuff going on within the spider diagram. I want to find the simplest one. Right there at the top. What is HX? What element is X? What is X? X is very commonly a halide. What we're referring to is HBr, HCl. Okay? What is special about HBr, HCl, or HI? That would be our halides, but here I'm actually saying HBr. There it is, it's a strong acid. What did you just say it was? A strong acid. How do acids react? Define an acid. An H plus donor. What's the first step? The pi bond comes out and shares with the hydrogen. Okay? What we're addressing is the most reactive thing, our HBr. That bond wants to shatter immediately, putting the electrons onto the bromide, because bromide can stabilize the negative charge better than the hydrogen. How do we stabilize the positive hydrogen? Well, we give it electrons from there. Where could that hydrogen go? Well, there's 2 carbons associated with that pi bond, so it could go to either one. Which one does it go to?
The one with the extra.
So what I asked about is where the hydrogen went, so you're saying the hydrogen goes there. Yeah? What goes to the other carbon? I haven't shown the BR do anything. So if you want to have the bromine do something, you would have to have the bromide come in and do something. It's not doing anything yet. What happened to our carbon? Did the hydrogen have to go to that position? Where else could it have gone?
It could have gone somewhere it's positive, but that's
Oh.
unstable.
Which carbocation was more stable?
Oh, shit. I did it backwards. Yeah.
Therein lies one of our potential issues. What we start talking about or focusing on is just the atom and not the charges. The charges are what dictates the chemistry. The hydrogen goes to the spot over here that leaves us with the more stable carbocation. What we showed in blue is technically wrong. It's not the likely result. Okay? Because what we were thinking is, oh, I put the hydrogen where I formed the most stable carbocation. Okay, well, let's walk through that. What charge is the hydrogen? Positive. What charge is our carbocation? Positive. Do I want the positive next to the positive? No. Where do I want the positive? Next to the negative. I want it with the electrons. So I want to put it in the opposite location so that I form the more substituted carbocation. Okay? Lots of kind of inverses that can go within that depending on what you're referencing as you navigate through. This is where drawing out reactions allows you to predict those charges. Allows you to have that conversation. As opposed to just rote memorization. Oh, I just put it on because I think it belongs there. The instant it's written down provides you that context to make that decision appropriately. Does that make sense? Okay. So that one was wrong. Does that change any of our arrows? Our electrons are still coming from the pi bond to that hydrogen. Still produces this. It's just where we decided to draw the hydrogen. So our arrows are still identical. No changes. Okay. Secondary product, or not secondary product, but byproduct, we would get this bromide, Br minus floating around. I also happen to have a positive, so what should I do? Hook them up. What do I get? What did we say X was? Our bromide. But we didn't show the hydrogen. We didn't have to show the hydrogen because it's implied. Okay? So those implied hydrogens come back and will haunt us and be like, well, I don't see where it went. You're not seeing where it went because it was implied within the structure. Kind of, sort of? Is there something else that we could do to help us predict this? Yes. So let's erase all that. What do I think with this eraser? What's the most reactive thing we have here? If I threw alkene at you, what are you going to do? I don't know. Are alkenes toxic? I throw hydrobromic acid at you. Motherfucker, you better not. Okay. Hydrobromic acid is a strong acid. That's dangerous. What's the most reactive thing? Hydrobromic acid. How is it reactive? It wants to donate H+. How do you know it wants to donate H+? Because it's a strong acid. That's what acids do, Mike. That's how they're defined. Why are they defined that way? Why is the hydrogen positive and the bromide negative? It's a polar covalent bond. That's an electronegative difference in there where the electrons go to the more electronegative element. So if we understand polar covalent bonds, we've got a description of that. We have a positive and we have a negative. Sweet. Okay, do I see a positive and a negative here? I don't. Unless maybe there was a way that we could potentially move electrons around. Are we allowed to move any of the electrons in that molecule? What does resonance allow us to do? Careful, not all electrons. Pi bonds. Do I have a pi bond? Yes, I do. So I can now look at that structure and say, oh, well, I could move those electrons here. And if I did that, I would get a negative charge there and a positive charge there. This isn't the best Lewis structure. Okay? But it is useful. This is the best Lewis structure. Okay? Because everything's neutral. This is now useful because it allows me to see some charges, and charges are reactive. Just like when we looked at HBr, we saw it as reactive because we saw a polar covalent bond where bromine takes the electrons, positive and negative. Why does that carbon take the electrons, though? Couldn't I have just as easily said that pi bond takes the electrons there? That's a perfectly valid resonance. Is that equally valid to the one in red? No, why not? Stability of what? If you're focused on the carbocations, that's a secondary carbocation versus a tertiary carbocation, which means both of these are bad resonance, like not good resonance, but this is the best or least worst resonance. The least worst resonance, if we remember all the way back in Unit 1, is what I called useful. Why is it useful? Well, what should we attach to the positive? Something negative. What should we attach to the negative? Something positive. And if we just established positives and negatives, what do we have? The flippin' answer. I don't need to know all the steps of the mechanism. I can just look at positives and negatives, connect the positives and negatives, and be done. Say, hell with it. There's an answer. That's lovely. Does that have massive holes in it? Yes, it has huge gaping holes in it. Okay, for instance, the structure drawn up top doesn't address some other issues that could happen with this. Okay, if we look at the drawn out kind of mechanism in a little bit more detail, we move through our red resonance contributor. We've got our hydrogen here and our positive charge there, and then the bromide with all of its electrons, right, comes in and attacks that positive. What was the positive? I know that's a weird question. What do you mean? What makes a positive? Where is a positive held? What did you say? Yeah, but where is the missing electrons? It's a p orbital. And what was the issue with p orbitals? They're above and below, which means where could this bromide come in? From above, meaning it would be wedged. Or below, dashed. Damn, we didn't specify that. Did we have to? When do we specify wedges and dashes? When there's a chiral atom. Is it chiral? No. What's problematic with the starting structure we picked? It doesn't allow us to see that added complication behind the mechanism. But if we start making that structure more and more progressively complex, it then makes it more and more difficult to actually draw appropriate spider diagrams. So some information is always going to be missing when we look at these diagrams. And it's going to come down to you deciding what part did you need to be relevant for it. Okay? That is a very hard question. Okay? One, I've not fully come to terms with how I'm going to test on. But the first and foremost thing that I think is most critical for you guys to be able to acknowledge is, can you find positives and negatives? How do I know you found that this bromide was negative? When you hooked it up with that positive, because that was the most positive. Right? So if I can get you to recognize aligning positive and negatives to get a predict a product, I'm happy with that. Would I be more happy if you also acknowledge where the stereochemistry is? Yeah, I would love that. That's a freaking pipe dream. Okay, at best. We don't have the time to be able to develop all that. Does that make sense? Okay, so should we test you on it? Yeah, why not? Let's make life miserable. Okay, so everybody close your eyes. Let's see. How many of you had memorized what was at the end of this arrow? Right, there's an arrow there. Did anybody think they've already memorized what it was out there? No? Okay. Don't look at me like you're asking a freaky weird question. You all are crazy brains sometimes. What's the answer?
That R, that stands for like a carbon thing, right?
Okay, so you don't like the R? Okay, fair enough.
So I'm not thinking about the R. So just like the BR did, the OH would go to the carbocation after the electrons.
Slow your roll.
Okay.
What's the first thing we should address?
Charge.
Yeah, let's find our positives and negatives. This was a new reagent, right? So is that one easy or hard? If it's new. Okay, hard. So don't look at that one, look at this one. Where's the positive, where's the negative? The exact same place they were for the last question, no difference. So, positive, negative, yeah? So now what do we got to find? Another positive and negative. So, do you see another positive?
Yeah.
Yeah? Where do you see that other positive? Ooh, okay, H plus. That looks like a good partner. So if we were to go through and look at an answer, we might go through and start kind of slowly piecing this together and say we're going to put the hydrogen right there, right? Because that was positive, negative. Cool. We found the positive. What do we need to find? The negative, right? And now we'll selective vision erase that because we don't care about that. That's the only thing we care about now. Do you see a negative?
See the partial negative.
Where do you see a partial negative?
Between the O and
Between the O and the H
Oxygen.
and the O and the C, right? All of those are partial, have partial negatives. Okay, if we were to draw that structure out a little bit more, you're saying you have a partial negative here because of electronegativity, right? Right? When we talk about our chemical reactions, it isn't just that we have a partial negative, it's that we had to have electrons there. Do we have electrons on that oxygen? Yeah? What do you mean? I have two lone pairs. Remember how we said that we tend to imply lone pairs on heteroatoms, but we got to remember to put them in? We do have those two lone pairs. Okay? So not only do we have a partial negative due to the polarity of that bond, but I got flipping electrons. So what could those electrons do? They could share with the positive. So what would I hope you'd be able to draw? I'd hope you'd be able to draw this. Okay? What's the funny face? Or are you just thinking it? Did you think it and figure it out? Yeah, okay. Is that a good drawing? Why is it bad? What? If we remember all of our Lewis structure rules back at the very beginning of the semester, right, we could go through and calculate formal charge. Or if we'd bothered to memorize the bonding patterns for oxygen, if it has 3 bonds, it is also positively charged. Does oxygen want to be positively charged? No. So what does it want to do? Get electrons. Where can it get electrons from? It could steal them from the carbon. Where else could it steal them from? Or from the hydrogen. Or from the other carbon. 3 possible answers. The blue one, you don't like. Why not? That goes backwards. I don't like going backwards. Let's go forwards. Okay, so the blue one's a bad idea. Green looks better. Why?
It's easier to take electrons from hydrogen
Why?
because carbon's more electronegative than hydrogen.
Fully accept that. Carbon's more electronegative than the hydrogen, which means the carbon's holding its electrons tighter than the hydrogen is. Which means oxygen's not going to be able to pull away from the carbon as easily. Which means the red one doesn't make sense. It makes sense to go after the green one, and we would get our final answer. Where'd the hydrogen go? It was implied. I don't have to worry about it. How is that different than what we just did? Hopefully what you can see, it's not. It's identical. That's the exact same thing we did with the strong acid. Okay? We do encounter some kind of secondary changes within this reaction. If we look at the reagent itself, it didn't say just HOR or HOCH. Okay? We had to add H+. Why? HO as a bond. Is that a strongly acidic bond? No. Okay? Because it's not strongly acidic, it can't react with the alkene. It's not positive enough to force the alkene to react. So what do we have to do? We have to add a strongly acidic thing to force it to react. Once it's reacted, it's now generated this positive charge, which I didn't show, Okay, but it generated that carbocation that really doesn't want to be a carbocation because it's missing its octet and is now frantically looking for electrons. That's where our oxygen can come in and share the electrons. This generates an unstable structure with a positive charge in the oxygen. The oxygen can quickly relieve that stress by stealing electrons from the hydrogen. Why is it stealing from the hydrogen instead of the carbon? Hydrogen's less electronegative than the carbon. Ta-da! There's an answer. What's the other answer? H plus versus CH3 minus. How often or how stable are each of those?
You mean CH3 minus?
If we had the oxygen steal electrons from the CH3 instead of from the hydrogen, we'd have CH3 plus versus H plus.
Okay.
Have you seen H plus before?
Yes.
Have you seen CH3 plus before? Technically you have. You have seen it in one case. It was in the case where we said it doesn't form. That's a zero-ary carbocation. We don't form zero-ary carbocations. Right? Which means, okay, we got to eject the H plus. What was the role of the H plus? I started with it and I ended with it, which means it was a catalyst. Pulling up, dragging up chem230 terms from chemical reactions. We have an acid catalyzed reaction. We need something positive enough to force the alkene to react. I didn't forget you.
Where did it go?
What?
Where did it go?
Where did what go?
H plus.
There's the H. Still there. It's implied. Oh, I see what you're saying. My bad. Where did this H go? Okay. That is actually a very good question that I would like to sidestep and dodge. Okay, and this becomes one of the kind of secondary issues within our chemical reactions. That H plus has to get picked up by something. That something has to have electrons. Where do we have electrons in the reaction? More of that alcohol. Okay, we still have that OCH3 floating around. That could share electrons with it. Does that make sense? We also still have alkene floating around. That could pick up that hydrogen. Okay. Typically what we would do is pick the alcohol to pick it up, not the alkene, because the alcohol is smaller and easier to draw than the alkene. So we pick the easiest thing to draw. Okay. I, as you noticed, didn't draw anything because I don't care what picks it up. I just know something picks it up. Okay. So anything with electrons in the solution could pick up that hydrogen because that hydrogen is extremely acidic. Okay. Because the oxygen does not want to be positive. Good question. Should have addressed that. My bad. Kind of, sort of? Oh, man. It gets worse. Sorry. Okay. Please do pack up. I promise. But I am going to talk over you. What we just looked at were all the acid additions. So anything involving an acid follows that exact same pattern. All of them. Okay? What happens when we move to something like BH3THF? There's our Lewis structure for BH3. Okay? Some things should stand out. Number one, it's missing an octet. It does not have a lone pair of electrons, which means its hybridization is something for you to determine this weekend. Right? And if it has said hybridization, there is something left over. That something left over should be reminiscent to the reactions we've just talked about. But that's where we'll pick up on Tuesday. Have a good Thanksgiving holiday. If you're not coming to lab. For those of you like, I don't have to come to lab. No, if you're in lab, you got to come to lab. Sorry.